So welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm grateful to welcome back tonight's speaker, John Baez. So given that I already introduced John last time, I thought I would share with you something new about him that you may or may not already be aware of. One thing that you may know about John is how active he's been in the development and public discussion of category theory. This is a topic once thought to be far removed from the real world. However, as just one example of its practical use, John and a group of collaborators at the Topos Institute have been developing software for epidemiologists. This software models the spread of disease with the use of concepts from category theory. Specifically, their software features what are known as stock flow diagrams that depict ODEs. If you're interested, please check out John's write-up on their project on his website, Azimuth. Now, John's first talk that he gave for our series was on the Tenfold way and included a discussion of Clifford algebras, types of Hamiltonians in physical systems, and associative real superdivision algebras. Tonight, he will be telling us about a geometric incarnation of the same story. His talk is entitled Symmetric Spaces and the Tenfold Way. Now, in order to keep things running smoothly for tonight's seminar, it would be great if everybody could please ask only clarification questions during the talk, and then it will be fair game to ask more expansive questions after John's talk. So John, anytime you're ready.
Sure, great. Well, thanks very much for inviting me back.
Pleasure.
I wasn't able to squeeze in the stuff about symmetric spaces last time, and I was really glad to be invited back to talk about this more geometrical aspect of the whole story. And it was even better that Cohl let me delay my second talk, because as I got embroiled in trying to prepare the talk, I realized that I needed to really sort out what was going on, that it was hard to figure out. And so that gave me enough time to figure out what I'm going to tell you. So I had mentioned last time that there's this beautiful pattern in mathematics with applications to physics, and first noticed by condensed matter physicists, that there are 10 of various types of things, and that these 10 things are all connected. There's a natural bijection between one of these sets of 10 and the others. So there are 10 kinds of real and complex Clifford algebras. I'll remind you what I mean by that. But basically, real Clifford algebra fold periodicity, and complex ones have twofold periodicity. Then a fellow named Wall, a topologist, showed that there are 10 associative superdivision algebras. Those are a generalization of the division algebras that you know and love to super vector spaces, that is Z-mod 2 graded vector spaces. So the reals, complexes, and the quaternions are 3 of those 10. But then there are also 10 ways that Hamiltonians can get along with time reversal and or charge conjugation symmetry. And indeed, it was in that aspect of things that condensed matter physicists got interested in this whole setup, and I think it was them who named it the Tenfold way. So they're all connected, and I tried to be explaining that, although it's quite a fancy story. But earlier in 1926, Cartan showed that there are 10 infinite families of compact symmetric spaces. And it turns out that these are also connected. So I want to explain how these 10 families arise from the 10 kinds of Clifford algebras. And in fact, this is already apparent in Milner's excellent book, Morse Theory, where he's explaining Bott's proof of the topological aspects of Bott periodicity, but he's just using it as a kind of tool to get to some certain end, a result in topology. And I want to expand on it as a thing in its own sake. That is, he's not deeply concerned with symmetric spaces. So what's a symmetric space? So it's a very symmetrical space. You may have heard of homogeneous spaces, which is a space that has a group acting on it in a way that's transitive, that maps any point to any other point. A symmetric space is a very special kind of homogeneous space. It's more symmetrical than just that. But in fact, we don't have to start out by mentioning anything about a group. We can define it just in terms of Riemannian geometry. So it's a connected Riemannian manifold such that every point has a map called inversion about that point. So it's a metric preserving smooth map from the manifold to itself that fixes that particular point. And on the tangent space of that point, its differential is minus the identity. So it reflects or reverses, you could say, directions about that point. So it just reverses everything. So a good example is a sphere of any dimension with its usual round metric. So that's a compact symmetric space. So the idea is if you're standing at any point on a sphere, there's a symmetry of the sphere, which leaves you fixed and reverses all directions about you. So it maps this blue arrow to this red arrow. And it also I should have maybe drawn some more arrows. It would map this sort of vertical tangent vector down to this one pointing downwards. So it completely reverses directions about that point. That's geometrically evident. But the fact is that every single point has such a symmetry. Now, there are a lot of other compact symmetric spaces, many of which are less obvious, but many of which are fairly well known in different contexts. So, for example, if you take the space of all subspaces of some dimension of Euclidean a Euclidean space of some dimension, that's called a Grassmannian. So, for example, the space of m-dimensional subspaces of Euclidean Rm plus n is called a Grassmannian, a real Grassmannian, and it's you can write it as a quotient of groups. So you take the whole rotation group of Rm plus n, well, rotations and reflections, the whole orthogonal group, and then you mod out by Om times On. So basically, this big rotation or / reflection group acts transitively on the set of all m-dimensional subspaces, and then the subgroup that preserves a particular m-dimensional subspace will be Om, because you can rotate that subspace any way you want, times On, because you can rotate the orthogonal n-dimensional subspace any way you want. So this is being described here as a quotient of groups, aka a homogeneous space. But it's better than your average homogeneous space because there is a way to do this reflecting about any point. So you can take any m-dimensional subspace and flip all the other m-dimensional subspaces about it, reflecting across it. And that makes it into a symmetric space. So Cartan, after he was done classifying simple Lie algebras, looking around for something else to keep him entertained, decided to classify symmetric spaces. He actually classified various kinds, not all compact, but I'm just going to talk about the compact Riemannian symmetric spaces. And he showed that there are 10 infinite families of those, all built using the real numbers, the complex numbers, and the quaternions, together with finitely many exceptions. I'm not going to talk much at all about the exceptional compact symmetric spaces, but I will just please you by pointing out that they're all built using the octonions, as you would expect if you're familiar with this kind of thing. So On is the group of rotations and reflections in a real Euclidean space. Un is the group of unitary operators, so that's the complex analog. Spn, sometimes called the compact symplectic group, maybe a better name for it, because symplectic means several different things. Maybe a better name for it is the quaternionic unitary group. It's just the analogous kind of unitary group of unitary matrices defined using quaternions. And there are various ways to stick these groups inside each other, and then you get various quotients that give you various nice spaces. I wish I had, I'm not asking to give another talk, but and I don't really want to give another talk, but nonetheless, I sort of wish I could give a talk where I just like lovingly explain each of these 10 kinds of spaces. Some of them are quite familiar. Others, like these Lagrangian Grassmannians, are mainly familiar for people working on particular subjects like symplectic geometry or so on, but they're all very nice. And so So it's nice that they fit into this framework. Now, last time I pointed out that there are also 10 kinds of real and complex Clifford algebras. Here, I'm taking Clifford algebras where I'm just throwing in more and more square roots of -1, and it loops us around here until we get back. And when we get back, actually, when we put in 8 square roots of -1 into a real Clifford algebra, we get the algebra of 16 by 16 real matrices. So we don't come back exactly where we started from, but we come back to an algebra that's a matrix algebra over the algebra we started from. And similarly in the complex case, but with period 2 instead of period 8. So Cliff 2 would be 2 by 2 complex matrices. So the real Clifford algebra, Cliff N, is to be precise, it's the algebra over the reals that's freely generated by n different square roots of -1, all of which anti-commute with each other.
Looks like John Huerta has a question. One sec here. Go ahead, John.
Hi.
Hey, John. I wanted some clarification. Are you defining symmetric spaces to have an inversion or like a reflection, or
I define them thus.
Okay. But the picture of the sphere, those look like reflections, not inversions.
Well, I said I should have drawn some more arrows. This map would map the red arrow to the blue arrow, but it would also map this arrow that I didn't draw going up this way down to this arrow going this way. Okay. So it's a product of 2 reflections. Yeah. Okay. It's an inversion. I call it a reflection, which is probably, I said that word, I shouldn't have said it. Yeah, it's like, yeah. So that's the real, that's the real Clifford algebra. And the complex Clifford algebra, we stick a little symbol for the complex numbers into its name, is the same sort of algebra, but we start with the complex numbers and then we throw in square roots of -1 to that, all of which anti-commute. But they all commute with the I in the complex numbers by virtue of what we mean by an algebra over the complex numbers. And so, as I hinted, we have these phenomena called Bott periodicity, although it was just, these were discovered before Bott. These were probably discovered much earlier by Chevalier or Cartan or someone, that when you add 8 square roots of -1 to a Clifford algebra, you get a new Clifford algebra that's just 16 by 16 matrices in the original one, and similarly in the complex case with period 2. And so this is a crude sense in which there are really just 10 different kinds of Clifford algebras. I'll say more about what I mean by kinds, but basically when you keep on going and get more Clifford algebras, the ones you get are just matrix algebras and the ones you had before. And also I should add, people start wondering, why aren't you putting in any square roots of +1? I know about more Clifford algebras with square roots of +1. Well, those additional Clifford algebras are also just matrix algebras over the ones that I'm talking about. So I felt no need to bring them into the game. They don't really add anything new to what I'm going to say. So the big question, though, is how do we get these 10 infinite families of compact symmetric spaces from these 10 kinds of Clifford algebras? What's the relationship between these two things? So the key, just to sort of outline the plan here, is to notice that Clifford algebras are a special kind of algebra called a star algebra, which I'll define, and to look at their star representations. Star algebras are a pretty popular framework for doing algebraic approach to quantum mechanics. So when you talk about like self-adjoint operators being observables, you're talking about an element of some algebra that's equal to its own star. And so we can distill the concept of what's going on to some pure algebra, and that's star algebra theory. So then it turns out that if we look at the real Clifford algebras, for example, we'll get a compact symmetric space if we take some star representation of some Clifford algebra, say Cliff N, and then look at the space of all possible ways of extending it to become a star representation of the next Clifford algebra, Cliff N plus 1. So that is, we already have this algebra with n square roots of -1 acting on some Hilbert space, forming a star representation, which I'll explain. And then we ask, okay, now I got an extra square root of -1. How can I get it into the game? And it turns out there'll be like different ways that next square root of -1 could act on our Hilbert space. And the space of all possible ways will be a compact symmetric space. So I want to explain that in a lot more detail. And I'll just mention that complex Clifford algebras work in a completely similar way. So I won't talk so much about them. They're just sort of an analogous case. Most people trying to introduce you to Clifford algebras will do the complex case, and then they'll say, well, the real case is similar, but it's like much more complicated. But I prefer the real case because it has more stuff going on, and then I can say, oh, the complex case is similar, but it's much more simple and boring. Okay, so what's a star algebra actually? So it's a real, for us, it's going to be a real algebra. So an algebra over the real numbers. I'm keeping it real, as they say in rap. Associative algebra. A with a unit. My algebra is always going to have a unit. And they're always going to be associative. Sorry, Octonian fans. Nothing for you today. And a star operation. And the key point about this star operation is that it gets along, it preserves addition, it preserves multiplication by real numbers, and it's, what do you call it? Sorry, I noticed I left out a property. I didn't say that if you star twice, you get back where you started from. So A star star equals A. I should have stuck that in there. And then we call this an anti-involution, meaning that it also reverses the order of multiplication. So if you're familiar with the transpose of real matrices, for real n by n matrices, for example, that makes that matrix algebra into a star algebra. It obeys all these properties. But I should say that, like, if I were doing the complex case, it would be a little bit fancier. I would have to put a little complex conjugate over this alpha here. That's the only difference. So what's a star representation of a star algebra? Well, since I'm keeping it real, I'm going to have it be on a finite dimensional real Hilbert space. And I don't want to do any infinite dimensional stuff today, so it'll be finite dimensional. All my Hilbert spaces will just be finite dimensional. So it just means a real vector space with an inner product. That's what I mean by a finite dimensional real Hilbert space. So what's a star representation of a star algebra on such a thing? So it'll just be a way of choosing a linear operator, rho of A from H to H, for each element A in our star algebra. And it has to be a representation in the sense that it gets along with everything. So namely, it gets along with addition, gets along with scalar multiplication, gets along with multiplication in the algebra. That's what we call a representation. But to make it a star representation, it has to get along with the star operation. So rho of A star is rho of A. Well, I could have written star here, but I thought you'd get confused by the abundance of stars. You'd start seeing stars. So I put a dagger here. So this is like physicists, I think, like to use the notation dagger. So if you have a map. Sorry, my slides are a little bit screwed up. So if you had an operator T going from H to H prime, then T dagger going backwards from H prime to H would be defined in this usual way that you define like the adjoint of an operator in quantum mechanics. The only difference is that we're working in a real situation, working with real Hilbert spaces. So for example, very concretely, if H was Rn, linear operators on H would form the n by n matrices, and then this dagger here would just boil down to being the transpose of a matrix. Don't even need to say conjugate transpose because we're working in the real case. So okay, so this is just saying that rho gets along with the star operation. Okay, then we can talk about when two star representations are sort of the same or equivalent, and there's a concept of them being unitarily equivalent. And it just means that, so you have a representation, say rho on some Hilbert space H, and a representation rho prime on some Hilbert space H prime. So a linear operator from H to H prime will be a unitary equivalence if, first of all, it intertwines the representation. So rho of A and then map it over by T is the same as first mapping by T and then applying rho prime of A. But then also we want this linear operator here to preserve the inner product. Probably I should have called this an orthogonal equivalence. So these equations here are the equations you see as the definition for a unitary operator when you're talking about an operator between complex Hilbert spaces. But we're dealing with real Hilbert spaces here. So the same equations say that you've got a map between real Hilbert spaces that has an inverse and preserves the inner product. And that would actually normally be called an orthogonal map between real Hilbert spaces. But because we're going to be dealing with different star algebras, sometimes the complex numbers, for example, I decided to just use the term unitary equivalence here. So the idea, in case you're like a physicist wondering what are all these definitions doing here, is that star algebras are a very useful framework for describing observables in quantum mechanics. And you can describe observables abstractly without having any Hilbert space around. And then you can look at a star representation of a star algebra and make them actually become operators on a Hilbert space. And then you're sort of back into the Hilbert space approach to quantum mechanics. So this is just a concept of an algebra of observables together with some incarnation of that algebra as operators on some Hilbert space. I see a question.
Yeah, Christopher's got a question. 1 sec.
Yes. You have to unmute yourself, Christopher.
Yeah, I'm trying to unmute him. Sometimes it takes a couple of tries for some reason. Here we go.
Yeah. Oh, just a clarification. Does rho have to map the identity of A to the identity operator?
Yes, it does. And I guess that's probably another mistake. Sometimes you can wangle out of it and have it follow from something else. But in this case, now that I think about it, it does not follow from this. So thanks very much. Yeah, I should.
Thank you.
So rho of 1 equals is the identity on H. Thanks. Yes, I want that. Right. So what I'm going to do is I'm going to make up a category, which is the category of all star representations of some star algebra A. And the morphisms in the category will just be the unitary equivalences between those. So for those of you who like category theory, this is a special kind of category where every morphism has an inverse. So that's called a groupoid. And so let's look at what we've got here. For example, R, the real numbers, is a star algebra where A star is just equal to A. Then a representation of R is just an action of the real numbers as operators on a real Hilbert space, but it has so many properties that it just turns out to have to be the usual action of the real numbers, namely by scalar multiplication. So there's no choice. So rep R just is the category of finite dimensional real Hilbert spaces. And then the morphisms between them are these things I was calling unitary equivalences, but as I already admitted in the real case, those just boil down to linear maps that have an inverse, which is the dagger. And those are usually called orthogonal transformations, at least among mathematicians. So it's just the space, it's just the category of real Hilbert spaces and orthogonal operators between them.
Looks like a couple of questions.
Clarification questions
Yeah, do you
thick and
mind?
fast. Yeah.
Go ahead, Bao. Oh, sorry. It always takes 2 tries for some reason. There we go. Go ahead, Bao.
Can I ask a question?
Go ahead, Bao.
Sorry. The question is, this whole construction, can I do it by taking, can you tell the states which you are using to find these Hilbert spaces and the GNS construction, and for the C star case? So let us say the
I
following.
think that's not a clarification question. I think that's like a can you do something that you're not doing question.
Yeah.
Sorry.
Can I ask you? The question is, there's a real form of this GNS representations using the Tomita operator.
Sure.
And the question is, can I get these real representations from the Tomita, finding the real Hilbert space and looking at the restriction of the complex representation to the real subspace?
I guess the short answer is I'd have to think about that. There's a complex version of the GNS construction and a real version, and there
It's
are
a real version of the real version.
But anyway, this is not at all what I'm trying to explain. Sorry. So I've got a lot of talk about, and I'd love to talk about everything else. And last time I think I talked, we had like about an hour of conversation after the talk, and it was tons of fun. But while I'm in the midst of explaining things, I'm trying to focus on trying to just talk about that. So if I start thinking about the real GNS construction, I'm gonna like completely forget what I was talking about. Sorry.
Would you so there's one more question. Did you want to take a clarification question, or did you want to move on?
If there are clarification questions, I'm really happy to answer it because I want people to understand what I'm doing here. Yeah.
Okay, so
yeah, just real quick. The word isometry comes to mind when you write T dagger T and T dagger equals identities. Why are you not using that word?
If the first, something that obeys the first equation is called an isometry, that means that it preserves lengths. But you can map a little Hilbert space into a bigger Hilbert space while preserving lengths. And that would be an isometry, and that would obey this first one. But an isometry that has an inverse also obeys the second one. And then you need some stronger word than isometry. And so I'm using orthogonal here, yeah. That's why I need to write both these equations, by the way, is to guarantee that T has an inverse, right? Because there are lots of maps that preserve length between vector spaces that don't have inverses. Okay, yeah. So there's R. Well, C is also a star algebra, where it's the star of a complex number is its usual complex conjugate. And then rep of C turns out to be the category of finite dimensional complex Hilbert spaces and unitary operators. Notice representations of C here means representations of C on, or star representations of C on real Hilbert spaces. But when you have a representation of C on a real Hilbert space, that makes your real Hilbert space into a complex Hilbert space, because now you know how to multiply by I as well. So we get complex quantum mechanics in this real framework by looking at representations, star representations of C. And then it turns out that for any star algebra, representations of that, star representations of that algebra form a category that's equivalent to star representations of n by n matrices in that star algebra. And that's why I sort of dismiss these cases when you have a Clifford algebra that's n by n matrices and some other Clifford algebra. They have equivalent categories of representations. Okay, now any Clifford algebra becomes a star algebra. The way you can do it is you make all these square roots of -1 be skew adjoint. That is, you define their stars to be minus themselves. That's the natural thing. So, because like square root of -1, you want it to be skew adjoint, just like in the complex case. So let's do that, and then look at this category of star representations of Cliff n for various n. So, well, as I said, Cliff 0 is R, so that its star representations give us real Hilbert spaces. Cliff 1 is C, so that's giving us complex Hilbert spaces. Cliff 2 equals H, the quaternions, and so you can show that we get quaternionic Hilbert spaces. If you don't know what quaternionic Hilbert spaces are, you can take this as a definition, but there is certainly a perfectly natural definition of that concept. When we get up to Cliff 3, then things get a little bit more weird or exciting. We get direct sum of two copies of the quaternions. And so the category of star representations of Cliff 3 is the category of quaternionic Hilbert spaces that are actually a direct sum of two orthogonal Hilbert spaces, V prime and V double prime. That's because of these two copies of H in here. I could have just called them pairs of quaternionic Hilbert spaces, V prime and V double prime. I'm just lumping them into a single thing and remembering the direct sum decomposition. Cohl pointed out that there is an algebra called the split quaternions. This has nothing at all to do with that, so perhaps this is an unfortunate name here. Then Clifford, we get 2 by 2 matrices of the quaternions. But its category of representations must therefore be the same as the category of representations of H. So we're just back to quaternionic Hilbert spaces again. So it's sort of like going back in time here. So Cliff 5 is 4 by 4 matrices of complex numbers. So its category, and I should say the star representations, is the same as that of C. So we're back to complex Hilbert spaces. Then Cliff 6 is 8 by 8 matrices in the real numbers. So again, we're getting real Hilbert spaces. And then Cliff 7 is direct sums of 2 copies of 8 by real matrices. So now we get what you could call split real Hilbert spaces, meaning real Hilbert spaces with a direct sum decomposition into 2 orthogonal parts. Or you could just call them pairs of real Hilbert spaces. And then, as I mentioned, after that, we just keep looping around. This category of star representations of Cliff n plus 8 is the same as that of Cliff n. By the way, if 2 star algebras have equivalent categories of star representations, you could call them Morita equivalent. And you can write this other kind of little squiggle between them to indicate that they're not necessarily isomorphic, but they're Morita equivalent. So if we keep track of things just up to Morita equivalence, the real Clifford algebras go like this: RCH, H plus H. But now I don't need to write 2 by 2 matrices in H. I just write H because that's Morita equivalent. And so we go back HCR, R plus R. You'll notice something wonderful and weird about this chart. I'm sure if you've thought about this stuff, that it has symmetry along this axis, but it's not the vertical axis. It's along this weird axis here. That will become important later. So we can look at their categories of star representations. In fact, we just did. And this is like a little review of the various categories that we get. Okay. So now here's the deal with symmetric spaces. If you have a star representation of Cliff n plus 1, it will restrict to a star representation of this subalgebra Cliff n. In other words, just forget what the last square root of -1 does. Just think about what the guys in Cliff n are doing. So you get a functor from representations of Cliff n plus 1 down to representations of Cliff n. That's usually called a forgetful functor because you're like forgetting what your last square root of -1 was doing. There's no technical definition of forgetful functor. It's just sort of a touchy-feely concept. You can tell when something is forgetting something if you've done enough of this stuff. So for any object in rep of Cliff n, you can ponder the set of ways that it could have come from some object of rep of Cliff n plus 1. That is, ways you could extend the representation of Cliff n to a representation of Cliff n plus 1. And by the way, I noticed that every time when I'm saying representation, I mean to be saying star representation. I'm just getting tired of saying it, I guess. So let's call that set F inverse of H, because it's sort of like the F inverse image of this object in here under this functor F. So here's the cool part. This turns out to be either a compact symmetric space or a finite union of compact symmetric spaces. That's how the compact symmetric spaces get into the game. Now, this idea is a bit subtle because how exactly should we define the set of ways that H comes from some object in this other category here? You might think it would be obvious. You just look at all the objects that map to this object here and they form a set. But actually, it's a little bit more slippery than that. And what I will do is only explain that if you want at the end. For now, I think I can get away with sleazing through this the way that like normal people rather than category theorists would be inclined to do. Whereas for the category theorists, they will delight in the subtleties that I'm going to not talk about right now. So I think it's more useful for normal folks to look at examples. So let's start at the beginning. So Cliff 0 is R, Cliff 1 is C. So their categories of star representations are the category of real Hilbert spaces and the category of complex Hilbert spaces, respectively. And this forgetful functor, what it's doing is it's taking a complex Hilbert space and giving you the underlying real Hilbert space. That is, you just forget that you know how to multiply by I. Just think of it as a real Hilbert space. You also take the inner product and you only take its real part, and that gives you a real inner product. So what we're doing now is the sort of reverse procedure. We're taking a real Hilbert space H, and then we're seeing ways that it could have come from a complex Hilbert space by this forgetful procedure. Or in other words, the set of ways it could be turned into a complex Hilbert space. So to take a real Hilbert space and turn it into a complex Hilbert space, you have to tell it how you're going to multiply by I in vectors in that Hilbert space. And that's called picking a complex structure. So what we're doing here is picking a linear map H, sorry, a linear map J going from H to H that squares to -1. But we want that multiplication by I to preserve the inner product. And I should have written the daggers here instead of stars. So we want it to be an orthogonal operator. We want J dagger equals J dagger J that equals the identity. So these are what mathematicians would call an orthogonal complex structure, although Milner just calls them a complex structure, and that's what I'm going to do too. So what we're getting here is the set of complex structures. So F inverse of H is just the set of complex structures on the real Hilbert space H. Now, if H is odd dimensional, there are no complex structures on it. There's no way to turn an odd dimensional real vector space into a complex vector space, because complex vector spaces always have even dimensional real underlying spaces. But if H is even dimensional, then there will be lots of these complex structures. You might as well just assume H is R to the 2n, it's isomorphic to that. And you can see that the group of orthogonal transformations of R2n acts on this set of complex structures, because if I have one complex structure, I can just conjugate it by any transformation in the orthogonal group and get another one. And this acts transitively. You can prove that that's not instantly obvious. And then the subgroup of it that fixes the standard complex structure on R to the 2n. I'm presuming you have some standard favorite way of thinking of R to the 2n as C to the n, and giving it a complex structure that way. That standard subgroup that fixes that standard complex structure is just UN, the unitary group. The unitary transformations, the ones that preserve the complex structure. So by the basic theorem on homogeneous spaces, this space of complex structures will be O to the 2n mod UN. And this is a famous space, and it's one of our compact symmetric spaces. So basically, I could run around this bot periodicity clock and do all 8 cases for you and show how they work out. But I'm not going to go into that much detail. So the next case, Cliff 1 is C, Cliff 2 is H. So now our forgetful functor is giving the underlying complex Hilbert space of a quaternionic Hilbert space. And this case is a whole lot like the previous one, so I won't spend much time on it. Now, F inverse of H is the set of quaternionic structures on a complex Hilbert space, and you can analyze what that is. And now you get that it's isomorphic to the group of unitary transformations of your complex Hilbert space H, the U to the 2n, if H was C to the 2n, modulo the subgroup that preserves the quaternionic structure, and that's the quaternionic unitary group, SPN. So that's another compact symmetric space. So they go on like this. Let me just do a case that's weirder. Well, luckily, the very next case is one of the weirder cases. So Cliff 2 is the quaternions, and Cliff 3 is quaternions plus the quaternions. So what this forgetful functor is doing is it's taking a quaternionic vector Hilbert space, I should say. The slides are full of typos. Hilbert space that's been written as a direct sum of two orthogonal pieces, like I'm showing here with my hands, right? That's what you should have in your mind. And it's just forgetting the fact that it's been split to two pieces and giving you the quaternionic Hilbert space. So F inverse of H would be just the set of ways of splitting H as an orthogonal direct sum of two pieces. So this is interesting because these two subspaces, they could have various possible dimension. If you started out with H to the n, an n-dimensional quaternionic Hilbert space, the first piece could have any dimension d going from 0 all the way on up to n. And then the other piece would have dimension n minus d. So F inverse of Hn is a union of different quaternionic Grassmannians. A quaternionic Grassmannian is just a set of subspaces of some particular dimension of a quaternionic subspace. And this here works out to be the space of d-dimensional subspaces of an n-dimensional quaternionic Hilbert space. So this is very much like the Grassmannian that I mentioned earlier in the real case. So now our F inverse of Hn here, it's not connected. It's a disjoint union of these connected pieces. And each of these connected pieces is what Cartan was interested in. He was interested in connected compact symmetric spaces. And so here we're getting a whole bunch of them all at once. So that's the weirder type of thing that can happen. And so this is the general story. So the theorem is that for any n, you have this forgetful functor. And if you take a star representation of Cliff n minus 1, the set that I'm calling F inverse of H becomes a compact symmetric space. And the same thing works in the complex case. And so you get a big bunch of compact symmetric spaces. And you get all of them in Cartan's classification of these infinite series. And I see this is slightly inaccurate here. I should say that you get either a compact symmetric space or a disjoint union of compact symmetric spaces, like we saw in the last example. So there are various mysterious things about this theorem, like, well, I guess the mysterious thing about every theorem is why is it true, right? So there are two questions here. One is like, why do you get a compact symmetric space? And then the other question, which is a much harder question, is why do you get all of the ones in Cartan's classification of infinite series? The first question I know the answer to. The second question, I don't really know the answer to, and I don't think anybody does. All we can say is like, look, I can look at Cartan's classification and then I'm getting everything in that classification. So that's why I know that we're getting them all. It's because I can just see that we're getting them all. But that's a crappy answer, right? Because you'd like to have like some really good conceptual reason why all series of compact symmetric spaces are arising from this construction. No one knows that as far as I know. If anybody does, I want to hear it. So okay, here again are these categories of star representations of the various kinds of real Clifford algebras. And then here are these forgetful functors. So the forgetful functors are generally pointing from representations of a Clifford algebra to a Clifford algebra with one fewer square roots of -1. But you'll notice, because of this funny symmetry that this chart has, remember I noticed that there's like a symmetry across this axis here, that here the forgetful functors are going, here the forgetful functors are going this way, quaternionic down to complex down to real, but here the forgetful functors are always going counterclockwise here. Here the forgetful functors are going the other way, real, complex, quaternionic. So they double back on each other. These are the forgetful functors on the first part of the chart, and these are the ones when they double back. And these forgetful functors all have famous names. For example, I talked about like the underlying complex Hilbert space of a a quaternionic one, or the underlying real one of a complex one, or so on. And then sometimes I'm taking the direct sum of the two pieces in a splitting to get the whole thing. So they all have various names. And I notice yet another typo. Every time I said vector space, I meant Hilbert space. That's what I'm really interested in. Yes, I have a question. Yes, you have to unmute.
Yeah, my question is, like, if we think of Clifford algebras as super algebras, then is the forgetful functor basically taking even or odd Clifford algebra and like reducing it to reducing one of the gamma matrices?
Reducing to what?
One of the generators of the Clifford algebra by considering only even or odd Clifford algebra.
That's a really interesting question. So my forgetful functor, I mean, my forgetful functors are coming from leaving out the last square root of -1 that we threw in, right? So any Clifford algebra like Cliff 3 will have a subalgebra like Cliff 2, where we leave out the last square root of -1. That subalgebra is not equal to the even subalgebra of your Clifford algebra, which I believe you were mentioning, but they are isomorphic to each other. They're isomorphic to each other as algebras, but they are not isomorphic to each other as superalgebras, because when we take the even part, we're getting a purely even superalgebra where everything left is even. Whereas when we leave out the last square root of -1, there's still a lot of square root of -1s in there. So there's still a lot of odd stuff. So this is one of the things that confused me for a while. That is, I would like to integrate this story with a superalgebra story, but it's really what I'm doing here, that I'm doing this different procedure of finding a smaller Clifford algebra and a bigger one by leaving out the last square root of -1. And that is not the same as the even part.
Okay, thank you.
Yeah.
Another question,
Another question.
Andreas?
Yes, when you leave out the last element of the generator of the Clifford algebra, are you setting it to 0 or are you setting it to 1?
I'm not setting it to anything. I'm not leaving out is not really a process, right? I mean, there's no mathematical operation called leaving out. So when I'm joking about, I'm talking about leaving out, but what we really have is that the smaller Clifford algebra is contained in the larger Clifford algebra. So there are algebra homomorphisms from each one down to the next bigger one. There aren't any. I don't want to think about.
You're ignoring it. You're ignoring it when you're forgetting. But what does it mean that you're ignoring it? That's what my question is.
Wow, it's really hard to define ignoring.
I mean, I can imagine like you could set it to 0, or I can imagine you could set it to 1.
It's not definitely not setting it to 0 or setting it to 1 or anything. No, because you could imagine like trying to get a homomorphism from a Clifford algebra to a smaller one by saying, okay, I'm going to take the last generator, I'm going to set it equal to 0. But if we did that, that would be disastrous. That would wind up setting everything to 0. In fact, that if you have
because you have products.
So no, we cannot think about it that way at all. There are no homomorphisms from these large. There might sometimes occasionally be, but we do not want to think about maps from the larger Clifford algebras down to the smaller ones where we're setting something equal to something. No, don't. But what we're thinking about are homomorphisms from the smaller ones into the bigger ones. But because we have a homomorphism from the small one into the bigger one, then a representation of the bigger one gives you a representation of the smaller one. That's how it works. So this representation.
Oh, it's on the representation level. I think that's where I'm.
Right. Yeah.
Okay. That's what I was getting wrong.
Okay.
Thanks.
Yeah. So what we're forgetting or ignoring is we had this representation of Cliff n+1, and we're just saying like, oh, I'll just forget that it was a representation of that, and I'll think of it as a representation or subalgebra. Yeah, that's right. Good. Yeah, it's important that the maps go backwards between the representation categories. Great. Okay, so we get all these maps, which obviously I could spend a bunch of time mulling over with you. And so we can just examine them and say like, okay, I'm interested in like the set of ways I can take a complex Hilbert space and think of it as extend it to becoming a quaternionic Hilbert space, or the set of ways I can take one of these guys and extend it to being one of these guys. And you get all these spaces, and here they are. So like the space of quaternionic structures on a complex Hilbert space would be U to the 2n mod SPN. And we get some Grassmannians, and we get others. We actually get the orthogonal and unitary groups as sort of somewhat special cases. But you will notice that when we've done this procedure, you notice that now the symmetry is very nice. It's along the vertical axis now. It just works out that way. Just in the sense that, well, I don't know what I even exactly mean by that, but yeah, that's probably not a very good thing to say, because there's not very evident symmetry in this chart, except for the fact that the groups are on the vertical axis. Something has lined itself up nicely here. And then you can do the complex case, and you get two more, which I'm just drawing in the same picture just for kicks. So let me just conclude with some remarks about the things that I haven't really gotten into. So as I mentioned, the correct way to define this F inverse of H is subtle. And the reason why is this: very often you'll have some representation of Cliff N, which when you restrict it to a representation of Cliff N minus 1, you don't get something that's equal to your H, but you get something isomorphic to your H. And normally the attitude in category theory is that should count as good enough. Isomorphic things count as being close enough to being equal that you should treat them with just as much respect. But the problem is there will usually be like loads of different choices of X that have F of X isomorphic to H. So if you just like count all of them as being elements of F inverse of H, you'll get way too many things. So the question is, when should you count two of such X's as giving different elements of F inverse of H? It's a subtle question, but luckily category theorists have figured this out ages ago. They have a name for this thing. They call it the essential fiber of the functor F. They know how to define the essential fiber of any functor. And if you click on this blue thing here, you'll get a link to the definition of essential fiber. So that's what you actually have to work with to really prove this theorem. Then the good news is that I finally came up with a simple proof that F inverse of H really is always a disjoint union of compact symmetric spaces. So the link between Clifford algebras and compact symmetric spaces is indeed a clear one, not a coincidence. But as I mentioned, what I did not yet come up with is some conceptual way to show that all the infinite series of compact symmetric spaces show up from Clifford algebras. So currently, the only way anyone seems to be able to do that is just check the list and notice that happens. This connection was first observed in a different sort of way by condensed matter theorists. I should emphasize that there are like a number of different papers in condensed matter physics where they relate Clifford algebras to compact symmetric spaces. They do it in ways that I think of as more complicated than what I'm doing. Namely, they look at spaces of fermionic Hamiltonians with various properties, and they get compact symmetric spaces. So it's very interesting in the physics application, but it's a little complicated. And anyway, more importantly, they just check and notice, hey, this is the same thing as Cartan's classification, without any real conceptual reason of why. So I think I'll stop here, and I will just either advertise or warn you that I have like secret extra slides lurking at the end of my slide deck. If you make the mistake of asking me more about either of these first two questions here, I will actually be able to answer you in as much detail as you want. Let's put it that way. I'll try not to answer in more detail than you want, but this is sort of the heart of the math stuff here. But I'll stop here while I'm ahead.
Thank you so much, John, for such a wonderful talk. I'll let people go ahead and raise their hand with questions. I've got one. I'm trying to understand the kind of the bigger picture of what's happening. So at the very bottom level, you've got Hilbert spaces, and then those are being acted upon by these representations of Clifford algebras. And there are 10 of these Morita equivalence classes when you view them as graded, right? There's 10 of those acting on these Hilbert spaces, but then you're saying now that the
go on. You just
okay.
Go on. I knew what your question was, but then go on.
Oh no, yeah. There's I need to set it up a little bit. So then now you're telling us that that in order to go from one of these Morita equivalence classes to another, this is how you're describing the symmetric spaces is getting you from one to another, and there are 10 of those. So it's kind of, there's kind of this hierarchy. There's Hilbert space at the bottom, and then these representations of these Clifford algebras. And then on top of that, the next level up are the symmetric spaces. So my question, so if that's correct, then my question is can you go one level higher, and could there be something that maps one symmetric space to another?
I'll have to think about that. There's definitely more stuff one can do with these symmetric spaces. Let me just mention something that like you made me think about. So the way I would think about it is that we're taking real Hilbert spaces as sort of like the basic starting point here. And then we're looking at different Clifford algebras. And if you like, you could think of them as, well, we are thinking of them as star algebras. And so you could think of them as like different possible algebras of observables in different forms of quantum mechanics. And then when we look at representations of those star algebras, we get various interesting refinements or extensions of the concept of real Hilbert space to like complex Hilbert space, quaternionic Hilbert space, and so on. So you can think of each of these representation categories as like as a kind of context in which you can do some kind of quantum mechanics, where we start with real quantum mechanics, and then like we get these more fancy kinds of quantum mechanics. And then there are these forgetful functors pointing around counterclockwise around this wheel, which say things like, well, if you had a quaternionic Hilbert space, you could just forget about that last square root of -1 and think of it as a complex Hilbert space, and so on. So there are so these are not like isolated worlds, these 8 worlds. They're maps from each one to the one around the wheel. And then the symmetric spaces are showing up when we just asked, given a guy in here, what are all the guys in here that could have mapped to it, basically, up
right.
to isomorphism or something. Yeah,
exactly.
And so then we get a space of such ways, and yeah. So that's the part I understand reasonably well. I should add that like we could have done fancier things, like we could have mapped twice, boing, boing, right? And then we could have asked, like, given a real Hilbert space, what are all the set of ways we could have made it into a quaternionic Hilbert space? So we could have formed these things called essential fibers of a composite of 2 functors. And we get very interesting spaces. They would not be symmetric spaces, but they would still be like some group mod some other group. So they'd still be quite nice. I don't really know everything to know about like how symmetric spaces fit into the game. But one thing you mentioned is you said the phrase 10 Morita equivalence classes. And there's something true about that, but you'll notice, right, that like here, we're not getting 8 different Morita equivalence classes
Right,
because we're getting real Hilbert twice.
Yes,
right?
yeah.
Yeah. So what's going on? So
There was a
so
grading, wasn't there grading?
right, yeah,
Two grading.
right. So in this, yeah, graded. So here I'm not looking at super representations or graded representations. Here I'm just looking at ordinary representations. And so then instead of getting 10 Morita equivalence classes, you get fewer. So these 8 boil down to I guess what is it? 1, 2, 3, 4, 5. And the 2 in the middle, there's still, I guess, 2 different kinds.
Would it not have worked if you would have kept the, would it have been possible to keep a Z2 structure in there?
I'll just, so that I don't spend forever hemming and hawing, I'll just say, like, I'm confused about that. I'm confused about that. There are, I could also make a chart like this, and should make a chart like this for the super representations. And then what we would see, weirdly enough, is that those categories of super representations, as this is going to confuse the hell out of you, so you wish you hadn't asked it. Those categories of super representations, as categories, they are equivalent to just these same ones, but listed in some other order. That's the first weird thing. And then the other thing is that as what you might call super categories, categories where the spaces of morphisms are super vector spaces, then there would be like all distinct from each other. So I will just say that, like, right now, bringing the super stuff into this, at first I thought it was going to like help me understand things, but then when currently it like only confuses me. In the end, it should probably somehow help. I definitely want to get it into the game.
Okay, and I guess it's kind of related to that question. So in your first talk, you were dealing with graded Hilbert, also Hilbert,
right,
as well too. So
yeah, especially there, because I felt like it was really to get the 10 in the tenfold way, right? So if I'd only gotten like, I don't know what, 7 things, yeah. It wouldn't have seemed very convincing. So, but even though I'm not 10 different kind of representation category, or 8 that I've shown here, even though I'm not getting the full complement of those, nonetheless, when we use them to make the symmetric spaces, we are getting the full bunch of them, right? We're getting all 10 of them. So it still deserves to be called a tenfold way, but we didn't need the super stuff to get these to all be distinct. Interestingly.
Okay. All right. I'll let somebody else ask a question here. John Barta, you're up next. Go ahead.
Hi. Thanks for this really interesting talk. I just wanted to ask about sort of the non-compact symmetric spaces. Like,
I don't know enough about them. So one thing I know very little about them. So you could probably spend your time more profitably just reading Wikipedia than letting me blather on about it. But I'll just say one interesting thing, which I don't understand at all, alas. Well, maybe I do, but just not enough. There turns out that each of these compact symmetric spaces has something called a Cartan dual, which is a non-compact symmetric space. And so Cartan also classified the non-compact Riemannian symmetric spaces, and but they fit into this story in some nice way. That is, they fit into this classification system in some nice way that he understood. But I have no understanding of them particularly, and I don't know like if you can efficiently get them from Clifford algebras or anything like that. That it might be possible to like take what people know about Cartan duals and ponder it, use some trick to get those non-compact guys from algebras too.
Can I offer my best guess about how to get them?
Okay.
Instead of looking at Hilbert spaces, look at spaces with a split signature in your product?
That might be the bit. What I know about what he does is it's something sort of like you take whatever compact Lie groups you had running around and you complexify them, and then you look at some non-compact real form of that complex Lie group.
Right.
That could be like a completely sympathetic to what you just said.
I'm guessing it is, although I don't know the
Yeah.
don't know the
Yeah.
story you're telling well enough to say.
Yeah, well, I don't know it well enough either. So I think I should just go back to the book sometime and try to ponder the non-compact ones more. It sounds like it would be a lot of fun.
Yeah, it sounds really fun. All right, so I wanted to add one more little thing. Is I wanted you to make good on your threat to expand on the concise proof that this is a disjoint union of symmetric spaces.
Okay, so let's see if I can do that without doing the first part.
You can also expand on the essential fiber. I'd love to see that
Well,
too. But,
no, then that's like unleashing the gates of hell or something.
No, it's not hell for me. You know that.
Yeah, well, I know, but it might be for other people. So it's sort of like telling the speaker, talk as long as you want about everything you like the most, but which is a dangerous thing you want to. So let me just try to do this second part and hope. Well, it won't completely make sense without the first part, but it will for a while. So the first thing is that the other way to think about compact symmetric spaces, that other than the way that I introduced at the very beginning of my talk, which is that you get them from compact simple Lie groups that have together with an involution, a homomorphism that squares to 1. And then the idea is you look at this subgroup of guys that are fixed by that involution. And then this quotient K is a compact symmetric space. And the idea of this inversion about a point that I mentioned in my original definition of compact space, the fact that this has a Riemannian metric just comes from the fact that G is Riemannian metric coming from the killing form. And so this quotient gets a Riemannian metric. But the fact that it has this inversion about any point is coming from this involution sigma. So for example, inversion about the identity point of G is just is this sigma here. So this is like, think about it. And oh dear, now here comes in the other stuff. So I'll try to, so what we do is that we, to get our compact symmetric spaces from Clifford algebras, is we take a representation of Cliff n-1 on H, and then we're looking at the space of all ways of this is going to be hard. I'm afraid I'm going to regret this because of the fact that, like, I was like trying to avoid giving the first part of the post talk, which introduces a bunch of terminology. So this is sort of bad, but let me just put it this way. Let me just say it super vaguely, because that's probably the best thing. Where the hell does this involution come from? It comes from this square root of -1. So if you have like the group of automorphisms of Clifford algebra with this extra square root of -1, it will be the same as of the smaller group of the smaller Clifford, the representation of the smaller Clifford algebra that commute with this last square root of -1, that commute with the row of En. And so you can describe that subgroup as being a subgroup that's fixed under an involution. And that involution is just, you take your automorphism of the smaller Clifford algebra and you conjugate it by this last square root of -1. Conjugating by a square root of -1 is an involution. If you do it twice, you get back where you started from. And things that are fixed by that conjugation are precisely the things that commute with that square root of -1. So that's how it works. I don't know if that made sense. It's probably best if you ask another question if you care, rather than I start like running back and trying to fill in all the notational.
So
Tells
H
that-
H is in the representations of Cliff n-1. And X
Right.
is
So what we've got here is
X is the thing that you're forgetting down to, right? Like
right.
okay.
Forgetting down from.
Sorry. Yeah.
This is a representation of Cliff n. When you forget that and think of it just as a representation of Cliff n-1, we're getting this thing I'm calling H. And we're asking, when are symmetries of H going to be symmetries of X?
Mm-hmm.
And the answer is when they commute with the last square root of -1 that we threw in. That one, if I'd explained this at all remotely well, that would be a very simple fact, but I'm not. So it may seem, and so then we can. So that's what I'm saying here. Rho is this representation here, and En is this last square root of -1. But that's the same, this subgroup here is the same as the group that's fixed by this involution, that's where we're conjugating by the last square root of -1.
So the candidate symmetric space that you get is odd H mod odd X.
Yes. And
And
if I had like shown all this, it's odd H minus odd over odd X. Here I'm talking about this where sometimes are things like a disjoint union of symmetric spaces.
Right.
But yeah, that's our candidate symmetric space.
Okay. And you get a disjoint union precisely when you have X's that are not isomorphic, but become isomorphic when you map them down to H.
Yeah, exactly. So like, yeah, exactly. Like in the case when we have when X is like a real vector space into a sum of two parts, there are different non-isomorphic ways to do that, which become isomorphic when you forget the thing and you just think of the vector space. Then we get this disjoint union of Grassmannians. Then each one of these quotients here is the Grassmannian, and we get a disjoint union of Grassmannians. Yeah. So sorry, that didn't work quite as nicely as I wanted, because I realized I did not make the second little mini sub talk be independent from the first. Oh well.
Well, maybe I'll let someone else ask for the other one if they want to. But I found that really helpful. Thanks.
Okay, sure. Good. They should just ask whether they're actually interested.
Sure. If they want to.
Yeah, or nothing at all. Yeah. Maybe Cohl, could you moderate these? Could you pick people to?
Yeah, the next person, sure. Okay, is you're up.
Okay. As I remember, Cartan also found that there are 10 different symmetry classes of random Hermitian matrices. How is this related to the tenfold way?
Yeah, it is related. I'm pretty sure it was not Cartan who discovered that. I think it was a much later discovery.
But I remember it was Cartan, but maybe
really?
I'm wrong.
Well, I'm astounded by that, because all the things I've read about random matrices tend to be from a later era. But anyway, I I can't give a terribly good answer to that, I'm afraid. So there are quite a large number of things that fall under the sway of the tenfold way. And if you want to like get a really exhaustive tour of them, which probably even includes what you're asking about, there's some very nice course notes by Gregory Moore, the famous mathematical physicist. There's it's like an unfinished book that's on his website where he goes through the tenfold way in many different guises, including some of the more physics influenced guises. And so I had mentioned that the tenfold way shows up in the classification of Hamiltonians with various kinds of symmetry under time reversal or under charge conjugation symmetry. And it turns out that from those 10 different kind of Hamiltonians, each one, you can use each of those to get you some ensemble of random matrices. I'm afraid I can't explain how, because I just don't understand it.
But
that is one
I think random Hamiltonians is related to symmetric spaces also. I remember something like this.
Yeah, that's definitely true. And that's the Hamiltonians, the classification of Hamiltonians in terms of symmetric spaces is explained in Gregory Moore's notes, as well as in various physics papers, but those notes are pretty systematic, the whole thing. So what I've been trying to do, actually, I'll admit, is sort of to get away from these interesting applications of the tenfold way and just try to get down to what I think of as like the basic thing behind it all. What that is, that's a somewhat subjective issue, but to me, I'm just sort of trying to focus on Clifford algebras and things like representations of Clifford algebras, and see if I can get these symmetric spaces as rapidly as possible from that. So this is, I think, a faster route to the symmetric spaces, but there are these more physics approaches that you're mentioning that also are definitely part of the picture.
Okay, thank you very much.
Sure.
I'd also be curious to know if the hierarchy can kind of be swapped around, like here you're getting the symmetric spaces from the Clifford algebras, but I wonder how much flexibility there is in
to get like Clifford algebras from symmetric spaces or something.
Yeah, exactly.
Yeah, I think that would be really interesting. I think there should be constructions where you start with a symmetric space and you build some algebras from it somehow that would be fun to look at. Okay. I haven't thought about that yet, but I should say that this research I did was just like I just finished doing it like about last week, so this is like the cutting edge of my knowledge.
It's a really rich topic. It looks like there's probably a huge number of different ways to think about it. So it's you can continue asking questions indefinitely. Okay, so Francis, I'll unmute you here. Just one sec. I'll try to unmute you. Okay, go ahead.
Okay, Prof. Thank you very much. I think I've gotten more enlightened with the topic, and I'm very grateful. I see the connection with what you're doing with that of an old paper that Pierre de la Hack did in 1972 on Clifford algebra, the spinors and the spinor groups of the Hilbert spaces. And he actually focused on the homotopy and the fiber bundles, the way they connect. That is specifically, he considered the classical Banach Lie groups, and he was able to look at the compact spaces or the symmetric groups more in that case. So I get a lot of revelation from your case and the Clifford algebras with what he did back then in 1972. Thank you.
Thanks. I'll have to read that. Was he studying any infinite dimensional Hilbert spaces?
Yes, he studied infinite dimensional on the classical Bernoulli groups. And
Right.
he did a lot of things with it. Yeah.
Yeah. So one interesting, thanks. Yeah, thanks for one interesting thing about this is that yeah, so in a lot of the stuff I've read about this, what people do is they take this idea here and they somewhat informally take the limit as n goes to infinity.
Yes.
And in this case, they might set m equal to n and then take the limit as n goes to infinity. And so then you get very, yeah, then, and you can do it formally. And then you get these interesting infinite dimensional spaces,
Yes.
which are basically, so this would be, yeah, you could make them into Banach manifolds, or you could be more like a topologist and work in a different framework. But here you get O infinity, they'd call it. And yeah, and so what as you probably know, what Bott was doing was he was looking at the loop spaces of O infinity, and he showed that the eighth loop space of O infinity is homotopy equivalent to O infinity. And so the first loop space would be would come from this. So it'd be sort of like O2 infinity mod U infinity and so on. And so also in going back all the way to Bott and to Milner's nice account of Bott's work, they're interested in taking a kind of limit as n becomes large. And also for the condensed matter physicists, where they're interested in systems with many degrees of freedom, they're also interested in n becoming large. So one of the things that I was doing that's slightly different is I was very much not taking any limit as n goes to infinity and just letting n be arbitrary, and then just noticing that then you actually get all the compact symmetric spaces when you do that.
Yours reveal a lot more because Pierre de la Have was actually not showing the Quaternion version. So he spoke about the nuclear octagonal. He called the octagonal group nuclear octagonal groups. And yours is much more revealing. So thank you.
Thanks. Great.
Okay, thank you. Andreas, I'm going to unmute you just one sec.
Yes, I'm curious about a spin structure. Like if you have intuition on how a spin structure could give intuition about what's going on here.
I don't know if I have anything great to say about that. So one thing you'll notice is that the spin group is not showing up at all here. Nor, I mean, the representations of the Clifford algebras, what they are is they're these, they're all direct sums of certain representations, which are called pinners. They're like spinners, but not with the S, meaning that they're like spinners, but they also know how to transform under reflections, not just under rotations. So pinners are lurking everywhere here. But I'm not using the fact that the spin group or the pin group acts on those pinner representations here. Okay. Here I'm just thinking of them as representations of the Clifford algebras. So I guess I'd say that there probably is a way to connect over to the whole business of spin structures, but maybe because I'm trying to strip everything down to some bare essentials, I'm not finding any need to bring that in here.
And any intuition just in general about all these flavors of Grossmanian, like why are they, what to make, I mean, your talk does that in a certain sense, but.
Well, what are they good for? Or what
well, why are there these different, I mean, what are these different flavors all about? You know, like what is it?
Yeah, I mean, it's like if you have 8 kids and you ask me like, what's the deal with all these kids? What are they all about? It makes me want to just like launch into a long story about each individual kid and beautiful particular charms, which isn't exactly an answer to the question, right? Because you might want a unified story, whereas I would be diving into particular details of these. Because I've been interested in all 8 of these spaces for a long time before I even knew that they fit into a common picture. And so I guess it will take me a while to like figure out how all that stuff I know is like somehow synthesized by this. So there are many, I guess I could say that like when you're doing quantization in different contexts, there are many cases where you need to pick a point in one of these spaces. So for example, and it may not be so evident that how that's working. So for example, suppose I'm trying to like quantize a particle in Rn, a particle whose configuration space is moving around in Rn. So its phase space is r to the 2n. The positions and momenta form r to the 2n. And we often do a thing called Schrödinger quantization, where we describe quantum states of the particle as wave functions that are functions of position only. So what we do is we look in r to the 2n and we pick the r to the n that describes the n position variables, and we do our quantization procedure starting from there, looking at wave functions on that r to the n. But you could have done quantization where you picked some other r to the n sitting inside r to the 2n. For example, you could have just picked the momentum variables and done quantization in the momentum representation. And you could have picked a whole bunch of other n-dimensional subspaces of r to the 2n and done the same thing. But you can't work with any old n-dimensional space of r to the 2n. You have to pick a space that's called a Lagrangian subspace of r to the 2n. And this thing here is the collection of all Lagrangian subspaces. So this is sort of the space of ways that you can pick some degrees of freedom of a particle in n dimensions and use them as the basis of a Schrödinger style quantization. And considering them all at once as points in this big space is a kind of thing that is interesting if you want to think about how your quantization procedure depends on the choice of the subspace. There's something called Maslow. I'm forgetting the name of it. The Maslov index. I'm mixing it up with like Maslow's hierarchy of human needs in psychology. But this is a Maslov. So there's a topological phenomenon that like you call the Maslov index, which is very important in quantization, that shows up from examining the topology of this. So that's a thing that you could go on for quite a long time about. But then over here, there are other approaches to quantization where what you want to do is you want to take your real Hilbert space and you want to think of it as a complex Hilbert space so that you can do what's called Fock style quantization. And so you may want to think about the space of all possible ways to do that. So at least in those cases, and probably in others if I thought about it harder, these spaces often show up as spaces of choices of a quantization procedure, ways of picking a quantization procedure.
Which goes back to this modeling choice.
Yeah, okay, yeah. So usually these are choices where like all the choices are isomorphic. So in some sense, it's not a big deal, but nonetheless, the fact that you have all these choices still exists and still manifests itself in some important ways. So maybe if I like really understood this stuff better, I could see that like all of the 10 of these things could be thought of as spaces of the parameterized quantization procedures. But I'm not at the point of being able to see that in a unified way.
That's great. That's very helpful. Thank you.
Nice. Okay, Christopher.
Hi, thanks for this delightful talk. It's really interesting. I want to just ask a simple question about, I think you called it theorem 2, that this inverse image under this forgetful functor is a a symmetric, compact symmetric space or a disjoint union, does that disjoint union have to be finite? You didn't
Yeah,
say
it will
finite.
always, it will turn out to always
Automatically.
be finite. And you sort of have to examine that by the case-by-case basis. I mean, the general abstract nonsense, which is this first junk that I've been avoiding, which is not really junk, could allow for cases where it was infinite. But in this case, the situations where you have choices are all of this Grassmannian flavor, where your choice is just a choice of some dimension from 0 up to the maximum dimension. So it's finite.
Okay, thank you.
Okay, Francis?
Yes, Prof. Please, I just wanted to come in with a question our colleague raised about this spin structure on it. Yes, with your representations, it has a spin structure because of the compact symmetric nature. When we take oriented Riemannian vector bundles over the M, we can have the second Stiefel-Whitney class to vanish, and when that vanishes, we consider a spin structure on it, which it agrees. Yes, so that's what I wanted to add.
Mm-hmm.
Yes.
Thanks. Yeah, that's true. Yeah.
Do we have any more questions? Well, now might be a good time to close things off. So thank you again, John, for such a wonderful talk. Yeah, that was
Great. Well,
really interesting. And thank you to everybody for so many really great questions. So I should mention that our next talk is scheduled in 1 week on the 22nd of May, Monday, 6 p.m. Berlin time, so back to the normal time. We've got Lev Weidman from Tel Aviv University speaking to us about the many worlds interpretation of quantum mechanics. So thank you sincerely again, John, for such a wonderful talk. You were able to get a very large number of questions tonight, so I think that's a really good sign.
Yeah, it was great. Thanks for all the questions. It's a lot of fun.